So last time we talked about the vector, parametric, and symmetric equation of a line. Now we're going to talk about the vector and parametric equations of a plane. So let's look at how do we find the equation of a plane in 3 space. Remember that if we wish to span a plane in 3 space, we need at least 2 non-collinear vectors. So let's call them A and B. If we want to hit another point on a plane, we need to start somewhere. So we're also going to need a point or a starting point, which we'll call P naught. We need an equation that will hit every point on a plane. So let's first start with a point on the plane. So let's say we want to find point P. Let's define it as a vector. So we're going to define it as OP. Another way to get to vector OP is to get to our known point P naught, so that would be vector OP naught, and using our triangle law, add a second vector which is in the plane, which we call P naught P. So we go from OP naught, we add P naught P, and that's the same thing as vector OP. So how does this help? Remember, we have 2 vectors in our diagram. We have A and B, which are in the plane. So we can take some scalar of A, add it to some scalar of B, and that would be the same thing as vector P naught P, this vector right here. So again, we're going to take some scalar of A, let's say Ka, add it to some scalar of B, let's say Lb, and that's equivalent to vector P naught P. So what we have is the following. If we want any point on the plane, point P, we're going to start with vector OP. And that is the same as taking our starting point, OP naught, and adding it to our 2 direction vectors. So K times vector A plus L times vector B. Now let's add our components. So our vector equation, x, y, z, that's our unknown point, or the point we're looking for, or just any point on the plane. We have a starting point, x naught, y naught, and z naught, plus our first direction vector in our plane, which we'll define as a1, a2, a3, plus a second direction vector in the plane, which we're going to call b1, b2, b3. So this is what we call the equation of a plane, and this is our vector equation. So again, to find the equation of a line, we need a known point in one direction. To find the equation of a plane, we need a point and 2 directions. So using the vector equation of plane, we can now get our parametric equation. And our parametric equation is determined by isolating for each of the components of the vector equation. So we get x equals x naught plus ka1 plus lb1. And then we go to our y component, so y equals y naught plus ka2 plus lb2, and z equals z naught plus ka3 plus lb3. And again, these are the parametric equations of the plane. So now we'll look at some examples using the vector and parametric equations of a plane. So example 1. Determine the parametric equations of the plane that contains the following points. A, -1, 3, and 8. B, -1, 1, and 0. And C, 4, 1, and 1. And then use the parametric equations of the plane to determine another point on this plane. So remember, to determine the equation of a plane, we need 1 point and 2 direction vectors. Right now we have 3 points. So imagine this is our plane. We have 3 points A, B, and C. So from those 3 points, I should be able to determine 2 direction vectors. Let's call them M1 and M2. So M1, looking at our diagram, is equal to vector AB. And remember, AB is the same thing as OB minus OA. So the components of vector AB are going to be 0, -2, and -8. So our second direction vector, M2, is equal to vector AC, and the components for AC are 5, -2, and -7. So there are two direction vectors for this plane. So if I want the vector equation for this plane, the vector equation of this plane is x, y, z is equal to, take any of the 3 points, so I'm going to take -1, 3, and 8, plus a scalar of our first direction vector. I'm going to say it's 0, 1, and 4. I don't want to use 0, -2, and 8, so I'm going to use a collinear vector, 1 and 4, plus a scalar of 5, -2, and -7. So again, for this here, I just took a collinear vector, 0, 1, and 4. So now that we have the vector equation, we can go to our parametric equation. So our parametric equation of the plane is x equals -1 plus 5L, y is equal to 3 plus k minus 2L, and z is equal to 8 plus 4k minus 7L. So there is our parametric equation for this plane. And finally, it says to determine another point using the parametric equation. And to find a point, all we have to do is let k and l equal some value. So let's say we let k equal 1 and l equal 1. Well, then we get that x is equal to -1 plus 5, which is equal to 4. Y is equal to 3 plus 1 minus 2, which is equal to 2. And z is equal to 8 plus 4 minus 7, which is equal to 5. So therefore, another point on this plane would be 4, 2, and 5. So again, here is the parametric equation of this plane, and using the parametric equation of the plane, we can determine another point on this plane. Example 2. Determine the point of intersection with the following plane and the x-axis. On the x-axis, the y and z values have a value of 0. So when a plane passes through the x-axis, the y and z values must equal 0. So with that information, we're going to have to find the values of s and t. So let's take out the values that we need. So we need the y value. So we know that y is equal to -2 plus 3s plus 2t. And we see that z is equal to -3 plus 0s and minus t. So remember that y and z are equal to 0. So I get 0 equals -2 plus 3s plus 2t. And for the z component, we get 0 is equal to -3 plus t minus t, which tells us that t is equal to -3. We can now sub that into our other equation. So we get 0 is equal to -2 plus 3s plus 2 times -3. And if we solve for s, we get s is equal to 8 over 3. So now we have our s value and we have our t value to help us determine when this plane intersects the x-axis. So let's sub these back into the equation for x. So we have that x is equal to, if we go back to our equation, x is equal to 6 plus 3s plus 2t. If we sub in our s value, you get 6 plus 3 times 8 over 3 plus 2 times -3. This gives us 6 plus 8 minus 6, which gives us an x value of +8. So therefore, this plane intersects the x-axis at the point 8, 0, and 0. So again, to quickly go through what we've done here, we want to know where the plane intersects the x-axis. So the key thing to remember is that the y and z components are equal to 0. So we sub 0 into the y and z components. We solve for t, we solve for s, and then we put that back into our equation for x to determine the x value. And our last example. Example 3. Determine the vector equation of the plane containing the point 1, -5, and 9, and contains the following line. So a good idea is to try to visualize what we have here. Plane contains the following point P, but then it also contains this line. And remember that a line has a point, which in our diagram, or which in our picture, is 1, 1, and 1. So we're going to add that to our diagram. And it has a direction, M. So we'll call that M1. And we can see that's equal to -1, 1, and 0. Equation of plane requires 1 point and 2 directions. We already have 1 direction and we have 2 points. All we need is a second direction vector. And we can get that second direction vector by using the points A and P. So that'll be our second direction vector, M2. So let's get our second direction vector. So M2 is equal to vector AP. So that's OP minus OA. So what we end up with is P minus A. So that's 1 minus 1. So that's 0. -5 minus 1 is -6. And 9 minus 1 is 8. So this could be our second direction vector, or we can use a scalar multiple. So maybe I just want to simplify this and do 0, -3, and 4. So we want the vector equation of the plane. We know it starts with x, y, and z, and that's equal to, we can pick any point. We can pick point A or point P. So let's say I pick point P. That's 1, -5, and 9, plus 2 direction vectors. So our first direction vector was -1, 1, and 0, plus our second direction vector was 0, -3, and 4. So there is the equation for this plane. It contains the point P and contains the line shown above. If you have any questions, please let me know. And please try the following questions.